Hello, my name is Addo, and today I'm going to be doing my exam presentation on plasma and cyclotron frequency. I will begin first by discussing what plasma frequency is. Plasma frequency describes the frequency of oscillations of charged particles, most often electrons because they are lighter than a lot of the ions in the plasma, when responding to small perturbations within the plasma or small disturbances from external factors that may have caused some charge imbalance. This is because of the restoring force that is present due to the electric field created by some sort of charge imbalance within the plasma. And this oscillation typically occurs at a length scale smaller than the Debye length, which provides us with the maximum length scale at which we cannot assume a plasma to display quasi-neutral properties, which is that the density of the ions and density of the electrons are roughly the same, assuming that they hold the same charge each. Another way of explaining the Debye length is that it is the maximum distance from the quasi-neutral region that an electron can travel within a non-neutral region before being stopped by the aforementioned restoring force, returning back to its equilibrium position. Let's take a look at this model of a plasma I drew, where we have a quasi-neutral region on the left and a non-neutral region on the right. The two sides are not drawn to scale, as the charged region is intended to be represented at a length scale of the Debye length, which will be smaller than the quasi-neutral region I have drawn. If we would like to find a plasma frequency, we must analyze the behavior of an electron that enters this non-net neutral region. There is an electric potential present at a length scale of the Debye length. This electric potential means there is an electric field produced. We can use this to compute the resulting restoring force caused by the Coulombic force of an electron entering this region as a function of the distance away from the quasi-neutral region. And this is done by applying Maxwell's equations. Maxwell's equation tells us that the divergence of the electric field is equal to the charge density over the permittivity constant. And then we put all of those together, the charge density equaling the number density times the charge over epsilon naught, and we integrate over x, which x represents the distance from the quasi-neutral region, and we eventually get a function of the electric field. We use this function of the electric field to compute the Coulomb force experienced by an electron entering the non-net neutral region. And this Coulomb force that we get, it takes the form of a simple harmonic oscillator, or linearly restoring force. So with this knowledge, we apply our understanding of simple harmonic motion, and then we eventually pick out the angular frequency from the equation of motion that we get from the force balance, and we eventually end up with the expression that the plasma frequency is the square root of the charge squared times the number density of the electrons over the electric permittivity constant. One of my favorite applications of plasma frequency understanding is the emission of radio waves and the impact of the ionosphere, which has a plasma frequency of the order of magnitude of about 10 to the 6 hertz. As we look at this image, we can see that daytime has a higher electron density than nighttime in the ionosphere. This means the ionosphere has a higher frequency at day than at night. If we view plasma frequency as how quick an electron responds to fluctuations in the plasma, the higher frequency daytime can reflect higher frequency radio waves. The one caveat is, though, that although lower frequency signals are still reflected during the daytime, AM radio waves, which are lower frequency signals, experience strong absorption in the D region. The D region is significantly weakened during the nighttime, however, in terms of plasma activity. So, AM radio waves propagate better at night. Now moving on to the next topic, which is explaining cyclotron frequency. Cyclotron frequency is the measurement of the orbital rate of a charged particle undergoing cyclical motion due to its movement in the presence of a magnetic field. I have shown here the derivation process for computing the cyclotron frequency. Assuming no electric field is present, we know from physics that any matter moving in a circle must have a centripetal acceleration represented by the speed squared over the radius of circulation, which in this case is the Larmor radius, which cyclotron frequency does not depend on explicitly, so it disappears in our equations. To the right, I have shown a visual of an electron moving with initial velocity v0 in a constant magnetic field that is going into the page. And then it follows that trajectory from its initial v0 vector. So why is cyclotron motion important? It provides us with information about how magnetized the charged particle is, how much influence a magnetic field has on a charged particle. If the Larmor radius is at a length scale much smaller than the characteristic length of the system, then the particle is magnetized. We can use a Hall thruster as an example. So the way a Hall thruster works is that it has a solenoid in the center, which produces a magnetic field that at the end of the solenoid, it has approximately radially outward magnetic field lines, and alongside the electric field that is in the axial direction. Both of these magnetic and the electric field together produce forces that affect the motion of charged particles in the Hall thruster. Right now, I want to focus on where cyclotron motion comes into play and magnetization. So cyclotron motion, when the cathode transmitter or cathode neutralizer emits electrons into the Hall thruster, we see that the electrons cling onto the magnetic field. However, what we don't see is that the ions are moving in the are clinging onto this magnetic field, but rather the ions are being projected outwards as soon as they latch onto an electron, right? And what this produces then, what this tells us then is that the ions are not magnetized and the electrons are. And we can see this through the typical properties of Hall thrusters, which have a characteristic length about like a centimeter to a decimeter, centimeter to a decimeter, and a typical Larmor radius of electron is inside the Hall thruster is usually about 10 to the negative 4 meters versus the ion is 10 to the negative 2 meters, which is about a centimeter, which is the same as the characteristic length. However, for the electron, it's much smaller, meaning that the electron is magnetized, and it definitely shows us why we don't necessarily need to worry ourselves about how the magnetic field is going to affect the ions as they move through the Hall thruster, because our overall goal is to try to get the ions to project out to take advantage of the exchange of momentum between the ions and the device that is using the Hall thruster. But thank you. That's all for my presentation, and this was very exciting to talk about, and I hope this covered a lot regarding plasma frequency and cyclotron frequency.